Hey, Mr. Harrod, Amendarian here. We're going to help you with the ideal gas law. The ideal gas law helps us make a relationship between pressure, volume, temperature under a single amount of set conditions here. Okay? The equation for the ideal gas law is PV equals nRT. P is the pressure, V is the volume, N is the number of moles. So we try to use the ideal gas whenever we have the number of moles, which is N. Okay? R is the universal gas constant. We'll go over that in a second. And T is the temperature that must be in Kelvin. Right, Kelvin. Darian, very good. Okay, so the conditions will not be changing, and you will not have initial and final values for this as well. Okay, R is an ideal constant here. This is one of the three R numbers here, and they're going to be on the formula chart. You don't need to memorize these. Okay. R is equal to 0.0821 liters atmospheres moles Kelvin, 62.4 liters torrs moles Kelvin, 8.314 liters kPa moles Kelvin. We have to play the matching game. We have to make sure our volume is in liters, our pressure is in atmospheres, N is moles, and T is Kelvin here. Or you can use torr here if the pressure is in torr and the volume is in liters, moles Kelvin, liters, kPa, moles Kelvin here. You have to match your units to what the PV, N, and T are. Okay? Remember, volume must be liters for this equation. Okay? Must be liters. Okay, there are other forms of the PV-nRT equation depending on what you're solving for. One of the formulas that makes a substitution is you could do N equals mass over molar mass. So they took this formula and substituted in for N, and they came up with PV equals mass over molar mass, RT. And there's another formula including density. So density is equal to mass over volume. So they took the mass over volume and replaced it with density here. Density will be in grams per liter for gases. Grams per liter for gases. Okay? So here we go. We should try to do one of these problems here. Okay. How many moles of oxygen? I'm looking for moles. That is N. So immediately I already know it's PV equals nRT. Must be put in a 500 milliliter flask. Volume is 500 milliliters. Cannot use milliliters. So you gotta go milliliters, milliliters, liters. 1 liter goes here. 1 times 10 to the third goes there. And we get 0.500 liters. So we're not even going to use that number. We're going to use 0.500 liters. And you'll see why in a second. 20 degrees Celsius. You're right. We cannot use 20 degrees Celsius. This is 293 Kelvin. And the pressure must be in 1.77 atmospheres. Okay. We are going to have to pick an R. R. Okay? You never have to find R, you just have to pick one. I'm going to pick one with liters, moles, kelvins, and atmospheres. Liters, atmospheres, moles, and kelvin. That's the one I'm going to pick. So I am picking my R to be 0.0821 liters, atmospheres, moles, Kelvin. Okay. Now I'm going to substitute into the equation here. Pressure, 1.77 atmospheres. Volume, 0.500 liters. N is N. R is going to be 0.0821, and then T is 293 Kelvin. Okay, how am I going to solve this? The variable's here, so I'm going to multiply on the opposite side of the variable here. So I'm going to multiply these two numbers. Now I'm going to divide by this number, and I'm going to divide by that number. And I'm going to get an answer of N is equal to 0.0368 moles of oxygen, which is the ideal gas law. Okay. Should we do another example, Darian? I think so too, Darian. We should do another example. Okay. Here we go. If the grams of helium, so this is mass we're starting off with here, is 1.17 grams of helium, okay, are put into 500 milliliters volume, 500 milliliters, I'm going to convert that over to liters. Didn't I do that back here? Oh yeah, I did. It's 0.550 liters, yeah. So we're going to use 0.500 liters in a container that is 10 degrees Celsius. You're right. We're not going to use Celsius, Darian. 283 Kelvin. What would the pressure be in torr? So we're looking for the pressure in torr. Okay, so here's where this becomes fun. Okay, so I don't have double P's or V's or T's or something like that, so I'm going to use a form of the ideal gas law here. Okay, so I am going to pick an R. Liters, torrs, kelvins, but I don't have moles. Oh boy. Well, here's the thing I can do. There's many ways to do this. Okay, you can take 1.17 grams of helium. We know the molar mass of helium is 4.00 grams of helium per 1 mole. And cancel those out. Right? Because we can go from grams to moles using the molar mass, using the tape. Right? We all know this is tape, right? Tape. Yeah. So I got 0.2925 moles. Okay. So now I'm not using the mass anymore because I got moles. So now I'm going to pick an R with liters, torrs, kelvins, and moles. Liters, nope, I'm picking that one. Liters, torrs, moles, I'm picking 62.4. Pick an R. Liters, torrs, moles, Kelvin. Write an equation. PV equals nRT. Okay. So then we have a P, which is what we're looking for. We have a V of 0.500 liters. We have an N of 0.2925 moles. We have an R of 62.4. And we have a T of 283 Kelvin. How am I going to solve this one here? Well, the variable's here. So I'm going to multiply all three of these numbers, and then I'm going to divide by this number. And I get an answer if I have it written down somewhere. If I round for sig figs, oh, the answer's right there, Mr. Harridan. Hello. Pressure of 10,300 torr, which is the ideal gas law. Okay. Now you could also could have used this formula as well. You could have used PV equals mass over molar mass RT. You will get the same answer if you use that formula. Okay. The only difference is you wouldn't have done the stoichiometry tape part there. Okay. Thanks, Darian. You're a champion too. Okay. Now, next problem here. What is the molar mass of a diatomic gas? So we're looking for the molar mass, which is G moles, down with the gangsters, of a diatomic. Remember, the diatomics are I bring clay for our new house. We remember those too, right? If 1.6 grams, so we got 1.60 grams, that's the mass. 500 milliliters, which is really 0.500 liters, that's the volume. Exert a pressure of 2,500 millimeters of mercury. We'll deal with that in a second. That's the pressure. At a temperature of 350 Kelvin. Oh, Darren, you don't need to bark. It's in Kelvin. Pretty quiet when they're in Kelvin. I know. Okay. So how are we going to solve this problem here? Again, we're going to have to find an R. Okay, so we're looking for an R here. So liters, atmospheres, moles Kelvin. Nope. Liters, torr, moles Kelvin. Nope. Liters, kPa, moles Kelvin. Okay, so that's a problem. Right? Because my pressure is in millimeters of mercury. But remember, there is 760 millimeters of mercury equals 760 torr. So when it says millimeters of mercury, it's really torr. So now let me go back and see if I can find one with liters torr. 8.0821 liters. No, 62. I'm going to use 62.4. Liters torrs moles Kelvin. Okay, so I'm not using the original form of PV equals nRT. We are going to use the form of PV equals mass over molar mass over RT. Okay, I'm going to try to make this a little bit easier for us here. I'm going to do some algebra first on this one before I solve it. You see molar mass is on the bottom here, and PV's over here. You can switch these two. It's a switcheroo. It's a proportion in disguise. Okay, so it is actually molar mass equals mass RT over PV. Okay, let's see what the mass is. 1.60 grams. R is 62.4. T is 350 Kelvin. Pressure 2,500 torries. Volume 0.500 liters. Okay. So remember, when I do this on the calculator, okay, no parentheses. And it's going to be a double divide. Double divide, because I have two numbers on the bottom here. So you're going to see me do... No, you're not going to see me do it. Maybe you will. 1.6 times 62.4 times 350 divided by 2,500 divided by 0.5. Ooh, I got 27.95, which rounds to molar mass of 28.0 grams per mole. G moles, down with the gangsters. This is the ideal with molar mass. Remember, this is a diatomic here. So 28 is 14.01 times 2, so I know that this gas is nitrogen. You did a great job too, Darian. Guys are champions. The legend is out.